Good morning, dear students. Today topic is concept of degrees of freedom. We know motions are three types. Here first one is translational motion. Second one is rotational motion. And third one is vibrational motion. Let us discuss first one, translational motion. Here, a bead sliding along a wire. Has 1 degree of freedom. So that is here f is equal 1. Here a bead sliding along a wire. That is, to describe motion of a bead we require one coordinate. So it have 1 degree of freedom. An ant moving on a board has 2 degrees of freedom. That is, here f is equal 2. Here I am taking, this is x-axis, this is y-axis, here it is z-axis. Suppose an ant moving on xy plane, so that is, here ant is moving on xy plane. So to describe motion of ant, we require two coordinates, that is x coordinate, y coordinate. So here degrees of freedom is 2. A gas molecule moving in a container has 3 degrees of freedom. That is, here f is equal 3. Here I am taking, this is x-axis, here it is y-axis, this is z-axis. So here it is a gas molecules. So here gas molecule moving in a container. So to describe motion of gas molecule, we require x coordinate, y coordinate and z coordinate. So this is x coordinate, this is y coordinate, this is z coordinate. So here number of degrees of freedom is 3. Second one is rotational motion. Let us consider argon molecule. It is a monoatomic molecule like a globe or a top. It can rotate about an axis passing through its center of mass. So this molecule rotate about an axis that passing through center of masses. So here moment of inertia is equal to mr square. Here r is small. So in monoatomic gases we can neglect moment of inertia. Hence we do not consider rotational motion of monoatomic gas molecules. Let us consider oxygen molecule. It is a diatomic molecule. It has 3 translational degree of freedom. It can also rotate about an axis passing through its center of mass. So, in additional, it has 2 rotational degree of freedom. Let us see. See here, oxygen molecule rotate about y-axis or in xz plane. So that is, it is horizontal rotation. See here, oxygen molecule rotate about z-axis or in xy plane. So here it is xy plane. So that is, it is vertical rotation. See here, oxygen molecule rotate about x-axis. Here r is very small. That is, moment of inertia is I is equal to mr square is approximately it is 0. Hence this rotational motion is not considered. So diatomic molecule have 2 rotational degree of freedom. Therefore the diatomic molecule has 2 rotational degree of freedom. Third one is vibrational motion. If the distance between 2 atoms remains constant with time, it is called rigid rotator. Here, the distance between 2 atoms remains constant with time is called rigid rotator. Rigid rotator has translation motion and rotational motion. In fact, atoms are connected by a spring. The atoms vibrate to and fro along the axis joining them. Here, the distance between atoms changes with time. Hence, it is called non-rigid rotator. So, a non-rigid rotator have translation motion, rotational motion and vibrational motion. the diatomic molecule has one vibrational degree of freedom. If diatomic molecule considered as a rigid rotator, then total energy is the sum of translational energy and rotational energy. That is, here E is equal Et plus Er. So that is therefore E is equal, here translation energy is what? Of m along x-axis, here Vx square, of m Vy square plus half m Vz square plus of I1 omega 1 square plus of I2 omega 2 square. If diatomic molecule considered as a non-rigid rotator, the total energy is the sum of translation energy plus rotational energy plus vibrational energy. Total energy is equal translational energy plus rotational energy plus vibrational energy. That is, total energy is equal Et plus translational energy Er plus Ev. That is, total energy E is equal 1 by 2 mvx square plus 1 by 2 mvy square plus 1 by 2 mvz square plus 1 by 2 I1 omega 1 square plus 1 by 2 I2 omega 2 square plus of m, here v is dx by dt whole square plus of kx square. So here it is kinetic energy and this is potential energy. Next one is law of equipartition of energy. In equilibrium, the total energy is equally distributed in all possible energy modes with each mode having an average energy equal to half kBT. Explanation. Total energy in translation motion is, that is Et is equal, we know 1 by 2 mvs square plus 1 by 2 mvy square plus 1 by 2 mvz square. So it have three modes. So according to law of equipartition of energy, each mode having an average energy, it is equal to 1 by kBT, that is half kBT. So this mode have energy 1 by 2 kBT. This mode have energy 1 by 2 kBT. So that is total energy in translational motion is, so here 1 by 2 kBT plus 1 by 2 kBT plus 1 by 2 kBT, that is 3 by 2 kBT. Total energy in rotational motion ER is equal, we know 1 by 2 I1 omega 1 square plus 1 by 2 I2 omega 2 square. Here I am taking polyatomic molecule. So it have 1 by 2 I3 omega 3 whole square. For diatomic molecule, it have only two modes. For polyatomic molecule, it have three modes. So according to law of equipartition of energy, each mode having an average energy equal to 1 by 2 kBT. So here it is 1 by 2 kBT. So this is equal to 1 by 2 kBT. Here this is equal to 1 by 2 kBT. So total energy in rotational motion is 3 by 2 kBT. Total energy in vibrational motion, so that is EV is equal, that is 1 by 2 m dx by dt whole square plus half kx square. According to law of equipartition of energy, each mode having an average energy, it is equal to half kBT. So this mode is equal to half kBT. So total energy in vibrational motion is 1 by 2 kBT plus 1 by 2 kBT, that is kBT. In polyatomic molecule, there can be one or more number of vibrational mode. Hence, total energy in vibrational motion is kBT. It is for one vibrational mode. EV is equal FKBT. It is for F vibrational mode. Next one is using law of equipartition of energy to find specific heat capacity of gases. Here I am taking first one, monoatomic gases. Each atom of a monoatomic gas has only 3 translational degree of freedom. According to law of equipartition of energy, average energy of a molecule is here it have 3 translational mode, that is according to law of equipartition of energy, each mode having an average energy equal to 1 by 2 kBt. Here it have 3 translational mode, that is 3 into 1 by 2 kBt, that is equal 3 by 2 kBt. From this we can write average energy of a mole. We know in a mole Avogadro number of molecules exist, that is here average energy of a mole is 3 by 2 kBt into N into Na. So that is equal, we can write U is equal 3 by 2 here Na into kBt. We know Na into kB is equal R, that is called 3 by 2 RT. We know molar specific heat at constant volume is Cv is equal 1 by mu du by dt. For 1 mole gas, that is equal, here Cv is equal, here mu is equal 1 mole. So that is du by dt, that is equal d by dt of, here u is equal how much, that is 3 by 2 RT, 3 by 2 RT. So that is equal, here 3 by 2 R is constant, take outside 3 by 2 R, here differentiation of T with respect to temperature is 1. So therefore Cv is equal 3 by 2 R. For monoatomic gas, specific heat capacity at constant volume Cv is equal 3 by 2 R. We know Cp minus Cv is equal R. From this Cp is equal, we can write R plus Cv. Here Cv is 3 by 2 R. That is 2 ones are 2, 2 plus 3, 5 by 2 R. That is 5R by 2. So therefore Cp is equal to here 5R by 2. For monoatomic gas, specific heat capacity at constant pressure Cp is equal to 5R by 2. The ratio of specific heat capacities gamma is equal, we know Cp by Cv, that is equal, here Cp is equal 5R by 2 by Cv is equal 3R by 2. So here R by 2 cancel. So finally we can get 5 by 3. Therefore, for monoatomic gas, the ratio of specific heats gamma is equal to 5/3. Here I am taking diatomic gases. Let us consider a diatomic molecule as a rigid rotator like a dumbbell. Here a rigid rotator have 3 translational degree of freedom plus 2 rotational degree of freedom. Total it have 5 number of degree of freedom. According to law of equipartition of energy, each mode having an average energy equal to 1/2 kBT. So each mode having a average energy that is 1/2 kBT. Here in rigid rotator it have 5 modes. So average energy of a diatomic molecule is here it is 5 into 1/2 kBT. From this we can write average energy of a 1 mole of gas. Is here it is 5/2 kBT into Na. So that is U is equal, we can write 5/2 Na kBT, that is equal 5/2 R. Na kBT is R into T. Therefore, for diatomic molecule, specific heat capacity at constant volume is, we can write du by dt, that is equal d by dt of, here U is equal 5/2 RT. Here 5/2 R is constant, take outside, that is 5/2 R. Here dt by dt, that is differentiation of temperature with respect to temperature, is 1. So finally we get for diatomic molecule specific heat capacity at constant volume Cv is 5/2 R. We know Cp minus Cv is equal R. So from this Cp is equal, take right side, that is R plus 5R by 2, that is called 2 ones are 2, 2 plus 5, that is 7R by 2. Therefore, for diatomic gas, specific heat capacity at constant pressure Cp is equal 7R by 2. The ratio of specific heat capacities gamma is equal, we know Cp by Cv, that is equal, here Cp is equal 7R by 2 by Cv is equal 5R by 2. So here R by 2 cancel. So finally we can get 7 by 2. Therefore, for a diatomic molecule, the ratio of specific heat capacities gamma is equal 7 by 2. For a non-rigid diatomic molecule, it has in addition a vibrational mode. Therefore, the average energy of 1 mole of gas is U is equal Na into 5 by 2 kBT plus here average energy of vibrational mode is kBT, that is equal, so Na into here 2 was the 2 plus 5, that is 7 by 2 kBT. So here U can be written as 7 by 2 Na kBT into T. So here Na kB is R, that is called 7 by 2 RT. Specific heat at constant volume Cv is equal du by dt, that is equal d by dt of 7 by 2 RT. Here 7 by 2 R is constant, take outside, so here dt by dt, that is 1. Therefore Cv is equal 7 by 2 R. Therefore, for non-rigid diatomic molecule, specific heat capacity at constant volume Cv is equal 7 by 2 R. We know Cp minus Cv is equal R. That is Cp is equal R plus Cv. So here Cv is 7 by 2 R, that is equal 2 ones are 2 plus 7, 9 R by 2. For non-rigid diatomic molecule, specific heat at constant pressure Cp is equal 9 R by 2. Here I am taking polyatomic gases. A polyatomic molecule has three translational degree of freedom, 3 rotational degree of freedom, and F vibrational modes. So average energy of a polyatomic molecule is that is here it have 3 translational degree of freedom, that is 3 plus it have 3 rotational degree of freedoms, 3 plus 3 into, according to law of equipartition of energy, each mode have average energy is 1 by 2 kBT, that is here 3 plus 3 6 modes, so the average energy is 1 by 2 kBT plus, and it have F vibrational modes, so that is F into each vibrational mode have average energy is kBT, so that is it can be written as 3 plus 3, that is 6 by 2, it is 3 kBT plus F kBt. Take kBt common. So remaining terms are 3 plus F into kBt. From this we can write average energy of 1 mole of gas is 3 plus F into kBt into Na. U is equal 3 plus F into here kB into Na is equal R into T. So we know specific heat at constant volume Cv is equal du by dt. So that is here du by dt into here U is equal 3 plus F into RT. Here 3 plus F R is constant, take outside. So that is 3 plus F into R. The differentiation of temperature with respect to temperature is 1. So here we get specific heat at constant volume Cv is equal 3 plus F into R. We know Cp minus Cv is equal R. From this Cp is equal R plus Cv. Here Cv is 3 plus F into R. So R plus 3R, that is 4R. So from this we can write Cp is equal 4 plus F into R. Specific heat at constant pressure Cp is equal 4 plus F into R. We know the ratio of specific heats gamma is equal Cp by Cv. Here Cp is 4 plus F into R by Cv is 3 plus F into R. So here RR cancel. So therefore gamma is equal 4 plus F by 3 plus F. For polyatomic gases, the ratio of specific heat capacities gamma is equal 4 plus F by 3 plus F.